Hello everyone, this is Abhishek KV. Welcome to my YouTube channel. I hope you are all studying well. Last class we completed the first two subtopics in third chapter, matrices. That is types of matrices and operations of matrices. And in this session I move on to the next subtopic, that is transpose of a matrix. One of the important subtopic in this chapter. What is the definition of transpose of a matrix? A matrix is a rectangular array of ordered rectangular array of numbers or functions. Transpose of a matrix. See, if I consider the matrix, say A is equal to 1, 2, 3. What is the order of this matrix? See, 1 row, 3 column. It has the order 1 by 3. 1 by 3. If I write 1, 2, 3. See, changing this row to this column. This row to this column. That is, by interchanging the elements of rows to column and elements of columns to rows. Element of rows to column and vice versa. Columns to rows. That is nothing but the transpose of a matrix. See, this is denoted by A dash. This A dash represents what? Transpose of A or A transpose. See, if I consider matrix A as order 2 by 2. Matrix A has order 2 by 2. If examiner asks if A is equal to matrix contains the elements 1, 2, 3, 4 of order 2 by 2. What is A transpose? See, I already told you. By changing the elements of rows to column and elements of columns to rows. That is nothing but the transpose of a matrix, right? So, this row, this first row becomes first column and this second row becomes second column. Changing rows to column and columns to rows. See, 1, 3, it is in C1, it changes to what? R1. 1, 2, it is in R1, it changes to what? C1. That is first row changes to first column. First column changes to first row. And second column 2, 4 changes to second row. And second row 3, 4 changes to second column. Is it clear? So this is nothing but the transpose of a matrix. I hope you are getting this. I am going to consider another example. See, if matrix A as 1, 2, 3, 4, 5, 6. This has order 1, 2, 3. 3 rows, 2 columns. This has order 3 by 2. Then, what is the order of transpose of this matrix? It is of the order 2 by 3. That is, changing rows to columns to rows. See, transpose of this matrix. 1, 2, 3 is in first column. It changes to first row. 1, 2, 3. Second row 4, 5, 6. Second column changes to second row 4, 5, 6. Therefore, A transpose, the order of the matrix A changes. Column changes to rows, rows changes to column. I hope you are getting this. By interchanging rows to columns to rows, or by interchanging the elements of rows to elements of column and elements of columns to elements of rows. That is nothing but the transpose of a given matrix A. I hope you are getting this. Okay? Please note down the definition. Yes. Then I move on to properties of transpose of a matrix. As we are all discussed about the properties of addition of matrices, subtraction of matrices, multiplication of matrices, right? So what is the properties of transpose of a matrix? See, the first property says A transpose whole transpose is equal to A. A transpose whole transpose is equal to A. For example, see, A is equal to minus 2, 4, 5. What is A transpose? See, changing this column to row. This is the transpose. Minus 2, 4, 5. The order 3 by 1 changes to 1 by 3. See, 1 row, 3 columns. This is transpose. Then A transpose whole transpose. See, again, if I take transpose of this transpose matrix, transpose matrix, this row changes to column. See, minus 2, 4, minus 2, 4, 5 is of order 3 by 1. This is equal to what? A transpose, all transpose is equal to A. Is it clear? Therefore, this is the first property. This is the first property. Then, what the second property says? K into A transpose is equal to K into A transpose is equal to K into A transpose. That is K A transpose is equal to K of A transpose. See, where K is what? Constant. See, if I consider matrix K into A, that is 2 into A, 2 into A, that is 2A is equal to 2 into minus 2, 4, 5. Minus 2, 4, 5. This is equal to what? Minus 4, 8 to 2. This is by what? Multiplication by a matrix. Multiplication of matrix by a scalar. What is the scalar here? 2. 2 is what? Any constant. Any constant. See, 2 into A. This is equal to what? 2 minus 4, 8, 10. This is 2A. If I consider 2 into A transpose, if I consider RHS, 2 into A transpose, see, this is equal to 2 into, what is the transpose of this matrix? Minus 2, 4, 5. Minus 2, 4, 5. This is what? This is equal to, so, minus 2, 4, 5. This is what? 2 into A transpose. If I consider the RHS, that is 2 into A transpose. 2 into A transpose. See? 2 into A transpose. What is 2 into A transpose? 2 into A is minus 4, 8, 10. This is 2 into A. 2 into A transpose. That is 2 into A transpose is 2 into A transpose bracket. Minus 4, 8, 10. Minus 4, 8, 10. If I take 2 as common here, 2 as common, minus 2, 4, 5. See, this is equal to 2 into A transpose. 2 into A, 2A transpose is equal to 2 into A transpose. So, where K is constant, here 2 is the constant. So, this is the second property. Yes. Let us move on to the next property. That is A plus B whole transpose is equal to A transpose plus B transpose. See, if I consider A is equal to minus 2, 4, 5 and B is equal to, if I consider this matrix 1, 3, 4, it is possible to add A and B? No, right? Why? Because to do addition, both matrices should have same order. So, if I consider B is equal to 1, 2, 3, see, this has order 3 by 1. This also has order 3 by 1. What is A plus B? What is A plus B? Minus 2 plus 1, minus 1. 4 plus 2, 6. 5 plus 3, 8. What is A plus B whole transpose? This is equal to minus 1, 6, 8. Changing this rows to column. Because it has only one column and 3 rows. Then it changes to 1 row, 3 column. This is what? A plus B. Transpose of A plus B. Let us check the RHS part. See, what is A transpose? Minus 2, 4, 5. This column changes to this row. Minus 2, 4, 5. And what is B transpose? This column changes to 1, 2, 3. Therefore, A transpose plus B transpose. This is equal to what? Minus 2 plus 1 minus 1. 4 plus 2, 6, 5 plus 3, 8. See, A plus transpose of A plus B is equal to transpose of A plus transpose of B. Both are equal. Equality by equality of matrices, A plus B whole. That is, transpose of addition of these matrices is equal to addition of transpose of A and transpose of B. Is it clear? Therefore, A plus B whole transpose is equal to A transpose plus B transpose. If your question is, sir, what happens B transpose plus A transpose? Yes, it is also same. Why? Because addition of matrices holds commutative property. Is it clear? Then I move on to the next one. That is AB whole transpose. That is transpose of this product A and B is equal to transpose of B into transpose of A. Transpose of B into transpose of A. Let us consider the problem. This is for 5 mark. Again, this is for 5 mark. Matrix A is equal to -2, 4, 5 and matrix B is equal to 1, 3, -6. Verify transpose of this product AB is equal to transpose of B into transpose of A. See, to take transpose of AB, first we should find what is AB, right? So, A into B. What is A? -2, 4, 5. And what is B? 1, 3, -6. 1, 3, -6. See, what is the order of A? It is of the order 3 by 1. And matrix B has order 1 by 3, 3 by 1, 1 by 3. A, this has order 1 by 3. That is B has order 1 by 3. A has order 3 by 1. See, number of columns of the first matrix to do AB, number of columns of matrix A is equal to number of rows of matrix B. Therefore, we are eligible to apply multiplication for these two. What is the final matrix? See, it is of order 3 by 3. See, 3 by 1 into 1 by 3 gives 3 by 3 matrix. How? See, A11, A12, A13, A21, A22, A23, A31, A32, A33. To find A11, first row, first column. See, -2 into 1. -2. First row, first column. A12, first row, second column. -2 into 3, -6. First row, third column. A13, minus into minus plus, 6 2s are 12. 6 2s are 12. See, again, second A21, second row, first column. 4 into 1, 4, 4 3s are 12, 4 6s are -24. Again, 5 1s are 5, 5 3s are 15, 5 6s are -30. This is what? AB. This is what? AB. But what we need? AB transpose of AB. This is equal to -2, -6, 12. This first row becomes first column. This second row becomes second column. And this third row becomes third column. Third column. This has order 3 by 3. Obtained matrix is of order 3 by 3. This is what? AB whole prime. That is transpose of AB. This is LHS. Let us check about what about RHS. See, remember this one. Remember this. That is AB transpose of AB is this one. Let us consider the RHS part. That is B transpose into A transpose. See, B is this 1 by 3. Then B transpose is 3 by 1. That row becomes this. First row becomes first column. Is it clear? Then A transpose. First column becomes first row. -2 4 5. -2 4 5. Again, see, this has order 3 by 1. This has order 1 by 3. Number of columns is equal to number of rows. That is, number of columns of matrix B dash is equal to number of rows of matrix A dash. Therefore, we are eligible to apply multiplication for these two. Therefore, see, the final matrix is also of order 3 by 3. Therefore, final matrix is also order 3 by 3. But we should check the corresponding elements are same or not. See, first row, first column. 1 into -2, -2. See, first row, first column element of matrix B dash into A dash is equal to first row, first column, first row, first column element of matrix transpose of this matrix AB. 1 into 4, 4. 4. 1 into 5, 5. See, -2, 4, 5. -2, 4, 5. 3 into -2, -6, -6. 3 into 4, 12, 12. 3 into 5, 15, 15. -6, -12, -2, 12. -6, 4, -24. -6, -30. See, therefore, Therefore, B dash A dash is equal to A B O dash. That is transpose of matrix AB is equal to transpose of matrix B into transpose of matrix A. Therefore, this completes the proof. That is, we have verified A B whole dash is equal to B dash into A dash. That is, transpose of matrix A B is equal to transpose of B into transpose of A. Please note. Yes, let us move on to symmetric and skew symmetric matrix. The definition of symmetric and skew symmetric matrix is based on the transpose of a matrix. That is, transpose of a matrix is a main basic tool to define symmetric and skew symmetric matrix. What is the definition? See, definition 1. A square matrix A, say A, is said to be symmetric. Is said to be symmetric if transpose of matrix A is equal to A. A square matrix. To define symmetric matrix, we should need the square matrix. What is square matrix? Number of rows is equal to number of columns. Is it clear? A square matrix, say A, is said to be a symmetric if transpose of that matrix should be equal to that matrix A. For example, see, if I consider matrix A is equal to 1, 2, 3, 2, 4, 5, again 3, 5, 1 or root 3. What is the transpose of this matrix? This implies A transpose. It is denoted by A prime or A transpose, A to the power of T. See, A prime. This is called transpose of A. What is transpose of A? According to the definition, changing rows to column and columns to rows. Changing this rows to column. 1, 2, 3. This rows to this column. This row to this column. Second row to second column. 2, 4, 5. 2, 4, 5. Again 3. 2, 4, 5. Second row becomes second column. Third row becomes third column. 3, 3, 5, root 3. See, 1, 1, 2, 2, 3, 3, 2, 2, 4, 4, 5, 5, 3, 3, 5, 5, root 3, root 3. Matrix A is equal to transpose of matrix. So, here, this implies transpose of matrix A is equal to matrix A. This is of order 3 by 3, square matrix. This also of order 3 by 3. Changing rows to column. Rows to column, columns to rows. It gives the same order because both rows and columns should be equal. That's why we should consider the square matrix to define symmetric matrix. Is it clear? A transpose is equal to A. Then that matrix A is said to be symmetric. Then I move on to definition 2. Definition 2. That is, a square matrix, say A, is said to be skew symmetric matrix. Skew symmetric matrix if transpose of that matrix A is equal to minus A. That is, transpose of matrix A is denoted by A prime is equal to minus A. For example, see, here to define symmetric, transpose of that matrix is equal to matrix A. But transpose of that matrix is equal to minus A. If you get negative of that matrix, then that matrix is nothing but skew symmetric. For example, if you consider 0, 3, 1, minus 3, 0, 5, minus 1, minus 5, 0. See, this is denoted by A. This matrix is denoted by A. What is transpose of this matrix? This implies transpose of that matrix. See, 0. See, first row become first column. 0, 3, 1. Minus 3, 0, 5. Minus 3, 0, 5. That is, second row becomes second column. Third row becomes third column. Minus 1, minus 5, 0. See, is A transpose is equal to A? See, first element of the that is first row first column element of matrix transpose A is equal to first row first element of the matrix 0 is equal to 0. But see, minus 3 plus 3, is it minus 3 is equal to plus 3? It is not possible, right? So here plus 1 minus 1. Again minus 3 plus 3, 0 0, 5 minus 5, minus 1 plus 1, minus 5 plus 5, again 0 0. See, so if I consider minus 1 common here, multiplication by a scalar. What is the scalar? Minus 1. If I multiply minus 1 throughout this, see 0. Minus 0 may be positive or negative. If I multiply the positive and negative, it remains same. 0. Minus into minus plus 3. Minus into minus plus 1. Plus into minus minus 3. 0 into minus 1, 0. Minus 5 into minus 1, plus 5. 1 into minus 1, minus 1. 5 into minus 1, minus 5. Again, 0. See, this is equal to A into what? Minus 1. That is minus 1 into A. What is minus 1 into A? Minus A. According to the definition, if A transpose is equal to minus A, then that matrix is called skew symmetric matrix. And here we should note that all diagonal elements of skew symmetric matrix are equal to 0. See, consider these diagonal elements, but in symmetric may not. If diagonal elements are equal to 0, then that matrix should be skew symmetric matrix. Keep remembering. Is it clear? So this is about the definition and example of symmetric and skew symmetric matrix. Please note down. Yes, let us move on to the results of symmetric and skew symmetric matrix. The first result says, for any square matrix A, number of rows is equal to number of columns A with real entries. A plus A transpose is symmetric. See, A plus A transpose is symmetric. A minus A transpose is skew symmetric. For any square matrix A with real entries, A plus A transpose is symmetric. A minus A transpose is skew symmetric. How? See, examiner asked me this question in 2017. Show that for any square matrix A with real entries, A plus A transpose is symmetric, A minus A transpose is skew symmetric. As you all know, the definition of symmetric and skew symmetric matrix: a square matrix A is said to be symmetric if A transpose is equal to A. A square matrix A is said to be skew symmetric if A transpose is equal to negative of A. Is it clear? Then, see, if I consider this matrix, consider this matrix A, if transpose of this matrix is equal to A, this implies A is symmetric. But here we need to prove what? A plus A dash, that is A plus A transpose is symmetric. See, if I consider A plus A transpose as the whole matrix, sum of these two matrices is the one matrix, and we need to prove it is symmetric. See, if matrix A is said to be symmetric if transpose of A is equal to A. If I consider, my name is Abhishek, if I consider Abhishek as a matrix, Abhishek as one matrix, if Abhishek is said to be symmetric, Abhishek transpose is equal to Abhishek. If Abhishek transpose is equal to Abhishek, then Abhishek is called symmetric matrix. If Abhishek is a matrix. Is it clear? So, similarly, if I consider addition of this matrix A and transpose of this matrix A is said to be symmetric. See, if I consider this whole, call this as C. Call this A plus A transpose is C. C is said to be symmetric. That is, A plus A transpose is said to be symmetric means C is said to be symmetric. We need to prove what? C transpose is equal to C. Is it clear? See, consider, let Let A plus A transpose is equal to C. This implies, what about C transpose? This is equal to A plus A transpose whole transpose. According to the property of transpose of a matrix, A plus B whole transpose is equal to A transpose plus B transpose. So this can be written as A transpose plus A transpose whole transpose. And then A transpose, what is A transpose whole transpose? Again, the first property. A transpose whole transpose is here. Again, we need to what? A transpose plus A. Since addition of two matrices commutative, A transpose plus A can be written as A plus A transpose. What is A plus A transpose? C. A plus A transpose is C. C transpose. Let's say C transpose is equal to C. I already told you. A matrix, a square matrix A is said to be symmetric if A is equal to A transpose is equal to A. If C transpose is equal to C, this implies what? C is symmetric. C is symmetric. What is C? A plus A transpose is symmetric. We need to prove what? A plus A transpose is symmetric. Hence the proof. Is it clear? Then we need to prove what? A minus A transpose is skew symmetric. What is the definition for skew symmetric matrix? A square matrix A is said to be skew symmetric matrix if A transpose is equal to negative of A. Right? A transpose is equal to negative of A. Let us consider A minus A transpose is equal to D. A minus A transpose is equal to D. Consider D transpose. D is A minus A transpose. What about D transpose? A minus A transpose whole transpose. Again by the property, third property of a transpose of a matrix, A plus B whole transpose. See, by A plus B whole transpose is equal to A transpose plus B transpose. Therefore, A minus A transpose can be written as A transpose minus A transpose whole transpose. See, by A transpose whole transpose is equal to A transpose minus A transpose minus A. See, is it equal to D? A minus A transpose is D, but A transpose minus A is take minus common. Then it becomes A minus A transpose. See, A minus A transpose is D. This is equal to minus 1 into D. Minus 1 into D. See, what is the LHS part? D transpose. If D transpose is equal to minus 1 into D is equal to minus D. If D transpose is equal to minus D, then D is skew symmetric matrix. This implies D is skew symmetric. D is skew symmetric matrix. If D is skew symmetric matrix, we took what? D is equal to A minus A transpose. This implies A minus A transpose is skew symmetric matrix. So we need to prove what? A minus A transpose is skew symmetric. Hence the proof. See, very simple. Very important for your annual examination. Is it clear? For any square matrix A with real entries, A plus A transpose is symmetric matrix. A minus A transpose is skew symmetric matrix. This is the first result in symmetric and skew symmetric matrix. Let us move on to the next result. That result says any square matrix can be expressed as sum of symmetric and skew symmetric matrix. Any square matrix can be expressed as sum of symmetric and skew symmetric matrix. See, if I consider the matrix A, not only the matrix, a square matrix A of order m cross m, number of rows is equal to number of columns. Is it clear? This can be expressed as sum of symmetric and skew symmetric matrix. From the previous result, if I consider the square matrix A plus A transpose is symmetric matrix, A minus A transpose is skew symmetric matrix. This result says any square matrix can be expressed as sum of symmetric and skew symmetric matrix. Any any square matrix A can be expressed as sum of symmetric and skew symmetric matrix. My question is it equal to A? See, A plus A transpose plus A minus A transpose plus A transpose minus A transpose get cancel. We are remaining with what? 2A. But we need what? A in LHS. So we need to consider half of this. See, if I consider this A plus A transpose, it is symmetric. Multiplication by a scalar 1 by 2, this is also symmetric. If I consider A minus A transpose is skew symmetric, multiplication with 1 by 2, that is real constant. 1 by 2, real number. 1 by 2 into A minus A transpose is also skew symmetric. Therefore, this is symmetric. We consider 1 by 2 into A plus A transpose is symmetric. 1 by 2 A plus A transpose, A minus A transpose is skew symmetric. Skew symmetric. Let us check. This gives the RHS. See, 1 by 2 into A plus 1 by 2 into A prime, that is A transpose, plus 1 by 2 into A plus into minus 1 by 2 into A prime. See, cancel. What is 1 by 2A plus 1 by 2A? Half plus half. This is 1 into A. What is 1 into A? This is equal to what? RHS. Therefore, any square matrix A can be expressed as sum of symmetric and skew symmetric matrix. If examiner asks, in this result, you may get in the question, let A is equal to 1, 2, 3, 4. Let A is equal to 1, 2, 3, 4. Express the given matrix. Express the given matrix as sum of symmetric and skew symmetric matrix. Sum of symmetric and skew symmetric matrix. Sum of symmetric and skew symmetric matrix. See, for any square matrix can be expressed as sum of symmetry. See, this is square matrix because it has the order 2 by 2, number of rows is equal to number of columns. What is the formula? Half of A plus A transpose. This is symmetric. Addition of A minus A transpose into half. That is half of A minus A transpose. This is symmetric. This is skew symmetric. This is skew symmetric. Let us check whether this gives the given matrix A or not. See, let us consider A. This one is A. What is? This is the question. Please write down. This is the question. This is the question for 3 mark. This is the question for 3 mark. Is it clear? Yes. I am going to consider the solution. I am going to consider the answer for this question. Given A. What is A transpose? Changing rows to columns to rows. That is 1, 2, 3, 4. 1, 2, 3, 4. See, what is A plus A transpose? A plus A transpose. See, this is equal to 1, 2, 3, 4 plus 1, 3, 2, 4. But we should consider what? Half of. So this can be multiplied by the constant 1 by 2. See, 1 plus 1, 2. 2 plus 3, 5. 3 plus 2, 5. 4 plus 4, 8. Into 1 by 2. Matrix multiplication by a constant. See, this constant can be multiplied by all these elements. See, 2 into 1 by 2. 1, 5 by 2. This also 5 by 2. 8 by 2 is 4. This is equal to what? Half of A plus A transpose. This is nothing but symmetric matrix. Let us find out. Please remember this. 1, 5 by 2, 5 by 2, 4. Half of A plus A transpose is equal to what? Half of A plus A transpose is equal to 1 5 by 2, 5 by 2, 4. Similarly, half of A minus A transpose is equal to what? Half of A minus A transpose. 1 minus 1, 0. 0 by 2, 0. 2 minus 3, minus 1. Minus 1 into 1 by 2, minus 1 by 2. 3 minus 2 plus 1. 1 into 1 by 2, 1 by 2. 4 minus 4, 0. I already told you. If diagonal elements are 0, then that is skew symmetric matrix. That is the hint. Please keep remember. Is it clear? Therefore, this is symmetric, this is skew symmetric. Addition of this, see, addition of this should give what? This matrix. Let us check. See, first row, first element of this matrix should be added with first row, first element of this matrix. That is symmetric matrix, skew symmetric matrix. 1 plus 0, 1. 5 by 2 plus, minus 1 by 2. 5 by 2 plus into minus minus. 5 minus 1, 4. 4 by 2, 2. 5 by 2 plus 1 by 2. 5 plus 1, 6. 6 by 2, 3. 4 plus 0, 4. See, this is equal to what? A. Half of. Therefore, any square matrix A can be expressed as sum of symmetric and skew symmetric matrix. Symmetric and skew symmetric matrix. Very important example. Is it clear? So, this is about the results of symmetric and skew symmetric matrix, and this completes your third chapter, matrices. Is it clear? Then, in this chapter, what we studied? First, we studied what? We studied types of matrices. Then, in the second part, we studied operations of matrices, and in the third part, we studied transpose of a matrix, and from this transpose of a matrix, we defined what is symmetric and skew symmetric matrix. What is symmetric and skew symmetric matrix, and this is the complete blueprint, that is complete syllabus which we are already studied in chapter 3. And from this, in types of matrix, you will get one question for 1 mark. One question for 1 mark, you should get in that 1 mark in this subtopic. And in operations of matrix, that is addition, subtraction, multiplication. And from that we studied what? Properties. Commutative property, associative property, distributive property. From this you will definitely get one question for 5 marks. One question for 5 marks. That is in part 2. And in transpose of a matrix, we discussed about symmetric and skew symmetric matrix, and we discussed the results. From these two results, you will get either proof or the problems on the second result. That is for 3 marks. One question, definitely. Totally, you have 3 questions in chapter 3 for 5 plus 3, 8 plus 1, 9. I already told you this chapter is not only important for this 9 mark. This is very important tool, basic tool to learn, to study the next chapter determinants. I hope you are all getting this. Please keep studying. If you have any doubt, please post your doubt to my WhatsApp number 9900423635. And this completes the third chapter, matrices. In the next session, I will come with the next new chapter, that is determinants. Thank you everyone. Bye bye.